dual title. One was mathematical foundations and also applications. And today, in fact, we're going to talk about the applications. So this is the second part. The first part was devoted to conceptual. I have to understand. Yeah, good. So it was devoted to conceptual and oops. Just 1 second. To conceptual and mathematical issues and associated with the gravitational waves in full nonlinear general relativity. And now, using those foundations, which complement other lectures on approximation methods, such as the post-Newtonian methods and so on. And next week, you'll be hearing about numerical relativity. And these lectures that I've given so far, the first 4 lectures, they provide conceptual and mathematical notions which complement the approximation methods and numerical relativity methods. But in this last 2 lectures, part 2, I would like to sort of discuss how these results in exact general relativity can be used as a diagnostic tools to test the accuracy of the waveforms. Now, this is a little bit of a jump, because previously what I did was, systematic in the sense of, starting with some assumptions and developing the subjects. I did not give all the details, but at least the conceptual structure was completely laid out step by step. Now, I have to introduce you to a lot of techniques and their limitations that have been used over the last 10 years by this community which creates the waveforms. And this community is the one which led to the discovery. This work led to the discovery of gravitational waves. Of course, one had to have the instrument, which is so sensitive, but in order to interpret the data accurately, one had to have these waveform models. And it took me more than a year to understand how this works. And so I'm really going to share my understanding with you. And this is really mainly used. My lectures are mainly addressed to mathematical relativists, so that they can understand both the ingenuity that went into creating these waveforms. There are many tricks and also great insights that we'll talk about, and also to sort of point out the limitations where mathematical methods can be used to improve these waveforms. Okay. So that is the purpose up here. And so waveforms. And so I given you the first famous waveform, the discovery of by LIGO-Virgo collaboration. This discovery actually took place on the first day that the detector came online for observation run, which is quite spectacular. And these discoveries of the compact binary coalescences by gravitational wave observatories, these discoveries were possible because of what they call matched filtering method. The reason is because the noise in these detectors is really quite large compared to the raw signal, and one has to dig out the noise, the signal from this noise. And in order to dig it out, what one does is one needs to have accurate waveform models, and then one matches them. And so we have got a whole bank of these waveform models. The signal comes, and this software very rapidly runs through the bank and finds out which one it matches to. And then that is what gives us the description, the parameters of the binary. What were the progenitors? They were neutron stars, they were black holes, what their masses were, what their spins were. And then using the waveforms and the numerical relativity, we also have kind of the posterior observables, and we can predict what the final mass should be and what the final spin should be. These are not directly observed. These are really deduced. So the theoretical waveforms of compact binary coalescences, which are parameterized, as I said, by initial masses, spins, which are the intrinsic parameters of the subject, of the system. You also need extrinsic parameters like how far the object is located, what direction in sky it is located, and so on. So using all these parameters, one can actually take a particular waveform such as this one, and one can actually match with the incoming waveform, and then one says that, well, this is what we observed. And here you sort of see the superposition of what is observed and the waveform model, that the prediction of the waveform model to which this was the best fit. And what one calculates, or what one matches, is the strain, which is, I've been mentioning this several times, which is the H plus, the plus polarization, minus I times the cross polarization, or in our language, it is a shear, the asymptotic shear, or in invariant language, the derivative operator D on scry. So for that particular space-time, what was the derivative operator D on scry? That is what is being measured here. And now what one does is one has the theoretical waveforms, and then, as I said, we have the observed waveforms of the detector, and the mass filtering enables us to dig signal from the noise for the discovery, and then to determine the intrinsic parameters as well. As well as the extrinsic parameters like the distance and the sky location of the binary. And then we got these deduced observables, which are called the inferred observables, such as the final mass and the spin for astrophysics. So for this, we need accurate predictions for sigma, or if you like, for this psi4 naught. And I was asked why psi4 naught is called generally the radiation field, because psi3 naught and imaginary part of psi2 naught also have information about radiation. And as I said, the derivative operator D, and in fact, has psi4 naught, the curvature of that has psi4 naught, psi3 naught, and imaginary part of psi2 naught. So the derivative operator has all this information, but still we focus on psi4 naught because psi4 naught is the one which feels like 1 upon r, and by, like in other theories, the field which was like 1 upon r is called the radiation field. Okay. So we need theoretical predictions with sufficient accuracy. But general relativity cannot solve the two-body problem exactly analytically, because I've got two compact objects, such as two black holes or two neutron stars or a black hole and a neutron star. They inspire from far away and then they merge. Well, we had to use a combination of analytical approximations and numerical methods, because there are three stages for this evolution. A long inspiral phase, which is sort of can last for roughly 100 cycles, which is all this inspiral phase that you see up here. Then there's a phase of merger, and then there is a phase of ring down. So the inspiral phase is a long phase in which the two bodies initially very far spiral in. And here one can use post-Newtonian approximations and perturbation theory in V by C, starting with Newtonian orbits. And you have heard about this post-Newtonian theory in Piot's lectures. Then the next phase is the merger phase, when the black hole or the two compact objects are very close to each other, and then they merge and form a single object. And that phase is highly nonlinear, and it's a very violent phase. And for this, we need full general relativity, because post-Newtonian approximation fails. The speeds are comparable to the speed of light, if you like. And as we'll see in a minute, various approximations that are made there don't work. And then, but the end of it, at this merger phase, at the end of it, we've got a single horizon, and you've got a huge luminosity. The peak of the waveform up here corresponds to the corresponds to the merger. And then the quasi-normal ringing, it is really after the single black hole is formed, it is violent, and then it settles down. And while it is settling down, it is actually, there is a quasi-normal ringing phase, which is really a phase which is, the word was kind of used very heavily by Chandrasekhar, the astrophysicist, and he always gave the analogy of a bell. If you take a bell and you hit it with a bell, with a gong, then of course, initially the perturbations, what the sounds that you hear will depend on where it was hit, what kind of gong you used, and so on. But very soon after that, what you hear is really the properties of the bell itself, and the disturbance properties, so to say, have gone out initially, and when the bell is then ringing, and that is why it's quasi-normal ringing. It's quasi-normal because there is a frequency, but there is also the amplitude is decaying. So if you like, you have got complex frequency, and that is the quasi-normal ringing up here. So here we've got a single black hole surrounded by radiation, and that quickly settles down, and we can use this perturbation theory around Kerr, and we can sort of basically use these so-called quasi-normal modes around Kerr perturbation theory to describe this phase. Now there are three, so we're to combine all these three things. So this is called the spiral phase, this is a merger phase, and this is the ringing phase. And so very often you will see MR in this waveform models, and that corresponds to the model which incorporates all these phases in spiral, merger, and ringing. So there are three avenues, the main avenues to produce these waveforms. One is called effective one-body approximation, where one uses post-Newtonian results together with some numerical relativity inputs. So one is sort of evolving post-Newtonian theory to some approximation, but then correcting it by using the exact numerical waveforms. Then second class of waveform models are called phenomenological models. And these are phenomenological interpolations. So here one works in the frequency domain. Here one was working in the time domain. In other words, in the physical space-time, one is looking at the waveforms in time, whereas here one is looking mainly at the waveforms in the frequency domain. And one sort of takes these waveforms, which might come from EOB or from post-Newtonian methods, and then stitch to them, which I'm going to talk about in a minute, with the numerical waveforms. So one stitches these two things together, if you like, and then looks at that waveform and approximates it, breaks it into pieces, and approximates each piece with analytical functional form. And if this can be done, and of course one then moves over the parameter space, namely the initial masses and spins that produce this waveform, and then one adjusts these functions and their coefficients according to the parameters to produce a waveform that cover a large region of this parameter space. The parameter space is 8-dimensional, and it's quite large, it's huge, and therefore one cannot really hope to cover it completely with, for example, accurate numerical simulations, and one needs these approximation methods in order to cover this parameter space, because we don't know which parameters the incoming signal is going to correspond to. And then finally, there are things called surrogate models, and these are the most accurate ones when they're available. Here, what one does is one looks at the numerical relativity waveforms, and then one extrapolates, given two numerical relativity waveforms for two different parameters, one extrapolates them just kind of numerically, one extrapolates them between them, and by filling in the parameter space. So I got some waveform for one parameter space, another numerical waveform for another parameter space, and these ones are literally just extrapolating to see what is the best way of bridging the two waveforms that are actually available to me. Now, this is a long summary. I'm just going to read it because it's really, as I said, it took me a year to understand many of these things. And this is a brief summary of what I have understood. And this is a brief summary of procedures that are used to create the waveforms in the post-Newtonian methods, numerical simulations, and then how they are combined in these three ways in these three models to create the waveforms. And typically to mathematical relativists, this comes as a big surprise by how much approximation methods or heuristics that are involved. But people have great intuition, and I have come to respect this intuition greatly. And if you like, it is a challenge to us to find out, to show why these approximation methods, why this intuition works as well as it does. So what I would like to do is to summarize this, emphasizing the conceptual issues, the key assumptions and approximations, and also their limitations. I want to emphasize that this is only a bird's eye view addressed to mathematical physicists, and therefore glosses over many astute steps and novel techniques, technical stuffs that has been used by the waveform community to create this model, which have been used to make these non-trivial advances. This material is based on joint work with Tommaso Di Lorenzo and New Kera. And the account is not up to date because I just basically stops when I felt that I got sufficient grasp. I am not kept up with all the constant new things that happen to improve the waveforms. I kept touch with some of them, but not all of them, not in an exhaustive way. Nonetheless, I think this material will enable students and postdocs to appreciate why non-trivial checks on waveforms are needed and how this purpose is served by the balance laws that I discussed in the last 4 lectures. The main focus of the community has been on the part of compact binary coalescence that is relevant to the sensitivity band of the current gravitational wave detectors. This translates to about 100 quasi-circular orbits. This is the in-spiral phase, where dynamics is expected to be well modeled by slow motion approximation of the post-Newtonian expansion. And the last about 10 to 15 orbits, for which the dynamics must incorporate strong field effects of full general relativity, and this is done through numerical simulations. In principle, one could use numerical simulations for the entire process for this 120 orbits or cycles. But the required computational time and effort would be too large, given that we need to cover an 8 and greater because we also have these external parameters associated with the where the binary is located, its sky location, distance and the sky location. So I got at least 8 parameters dimensional space. And that is why a stitching procedure is used to take the post-Newtonian orbits and the post-Newtonian waveforms and then stitch them with the numerical waveforms. And now I'll explain to them what stitching means in the next slide. So the waveforms coming from post-Newtonian orbits and the late waveform from numerical simulations are stitched together to produce a waveform which covers all the phases. The result is often referred to as hybrid waveform. And in addition to a number of strategies, namely the effective one-body method, the phenomenological interpolation, and then numerical and surrogate models, they have been used to enhance the reach of the analytical waveforms and or to interpolate between parameters used in numerical simulations to create a large bank of waveforms. And to most of the theoretical people, mathematically oriented people, it comes as a big surprise that already there are a few thousand compact binary coalescence numerical simulations, but the data bank that LIGO Virgo routinely uses to identify identify a signal and then to estimate the parameters. It contains waveforms which are about 100 times that. So several 100,000 waveforms are there, and the computer then goes through, given an incoming signal, computer rapidly goes through and tries to pick out which of these waveform is best matches whatever the observation shows up here. So, I mean, it's 100,000. It's a large number of waveforms that have been created. The full bank used by LIGO Virgo collaboration for detection is this, for parameter estimation and for testing general relativity. I've given references at the end. So people interested, I urge them to look at them, at least abstracts and introductions, to understand where we are, how we got there, and what the future prospects are. There are really severe limitations, and one has to overcome them for the detectors that are going to come online pretty soon. So I urge mathematically oriented people to try to understand it so that they can make really valuable contributions to the surface. So let us begin first with the post-Newtonian expansion, and that corresponds to the in-spiral phase. And so this is essentially a Taylor series in small velocities, as you learned in the lectures on post-Newtonian theory. And that is truncated to various V by C orders. Now, the Taylor series itself is known not to be convergent, but this is also the case for QED. The perturbation series does not converge. But in QED, it is an asymptotic series. But here we don't know if it is actually an asymptotic series. As far as I know, this has not yet been shown. Maybe something was done more recently. If so, maybe one of you can correct me. But it's kind of generally believed that it is an asymptotic series. So for example, the problem is difficult because, for example, for luminosity of gravitational waves in the extreme mass limit, when one black hole is very large mass compared to the other one, it's like 1,000 to 1 or 10,000 to 1 or 100,000 to 1. The contributions up to V by C to the 4 and V by C to the 5, these terms go in the opposite directions. So if you just had, and so often, V by C to the 3 might be a better approximation than V by C to the 4, because this contribution went in the opposite direction and brought back us to closer to V by C. So these things are subtle, is the only thing that I wanted to indicate up here. And consequently, even when one can carry out calculations to high order, it is not easy to systematically control the truncation error. So if I cannot just say I cannot just say that V by C to the 5th is this, and therefore the next term is going to be smaller. I don't know that. I don't know that for sure. People have good intuition and people work with that intuition, but this is not something that is established clearly. So second issue goes under the name of Taylor approximants. The post-Newtonian waveforms are obtained by starting with the post-Newtonian expansions of energy of the system, E as a function of B by C, and the flux of radiative energy, F as a function of B by C. However, because the procedure involves the rational rather than polynomial functions, so you get a ratio of two polynomials, if you like, the functionals of E by C and V by C, there is actually some freedom in expanding out these quantities to obtain the waveform to a given post-Newtonian order. Because of rational thing, then the question is, which term are you going to expand first? And there are some ambiguities up here. And this is the so-called ambiguity in the choice of the Taylor approximants. If you could sum over the whole in infinite series, then it would not matter. But because you're truncating at some order, it is not obvious. Not all the approximants have the same accuracy. And in fact, the accuracy can vary from one region in the parameter space to another region in the parameter space. And one has to really have good understanding of all these things. And in fact, for unequal masses, this using which of the Taylor approximants you choose is generally the largest source of errors in the post-Newtonian waveforms. Again, as I said, by now there's enough intuition to know which is the best available approximant in a given region of the parameter space. But again, these are all based on a lot of experience, intuition, comparison with numerical relativity, and so on. And finally, in the post-Newtonian literature, there's a fixed background Minkowski space to all orders, and the post-Newtonian solution is assumed to be stationary, absolutely stationary in the distant past, before a time t less than minus tau is some given time early on. This assumption would seem unreasonably strong to mathematical relativists, since the sources for which the initial value problem is well posed in general relativity. If a solution is stationary in the past of a certain Cauchy surface, in the strong sense, then it is stationary everywhere. However, the post-Newtonian strategy, in this strategy, the system is non-stationary in the future due to the radiation reaction effects, and the assumption of past stationarity serves to make various tail terms finite. I think you had some discussion of these tail terms in the post-Newtonian lectures. The viewpoint is that the past stationarity is appropriate for real astrophysical sources of gravitational waves, which have been formed at a finite instant of time in the distant past. I mean, after all, we're approximating all these things with an asymptotically flat space-time, but the system didn't exist forever. System was formed in the distant past. And so the statement is that, yes, I'm violating some fundamental principles up here, but still, for the realistic system, I'm getting a better approximation. So people really assume that the system is stationary to the past. The physical idea behind this strategy is that the two bodies become gravitationally bound at a finite time in the distant past, while being still very far away from one another. And it is argued that the metric perturbation of the background in Kasky space can be taken to be stationary before this time, before they become bound, before the capture occurs. Again, this is a delicate subject about how the past is really treated, but I just want you to be aware that it is a delicate subject. And in the review articles, for example, you will see this assumption being made explicitly. In lectures, in the lectures that I'm giving, 5 and 6, we'll use much weaker condition. We'll not assume it is stationary in the distant past, but we will assume that the stationarity holds only in a limiting sense. And this assumption is mild and is expected to hold on physical grounds for compact binary coalescences, although not for scattering situations. So I'm here really focusing on compact binary coalescences rather than situations in which two black holes come in from infinity, scatter off each other, and go out again to infinity. I'm not considering that situation. We can discuss this in the discussion period if you are interested. In particular, this assumption that we are going to use, the weaker condition, is perfectly compatible with the non-stationary solutions of full general relativity. I'm not avoiding anything which says that the solution must be stationary in the future if it satisfies some conditions. I'm not assuming such conditions. I'm only assuming very weak conditions which perfectly allow non-stationary solutions in full general relativity in the Cauchy problem in the future. Now, in numerical relativity, one encounters different types of errors. So I'm now going to go through numerical relativity, and then I just talked about the post-Newtonian theory, and now I'm talking about numerical relativity, and then we'll talk about the waveforms, waveform models. So in numerical relativity, as I said, this is of course much more accurate because one is solving full Einstein's equation, and one really has two horizons, and these two horizons are going away, and then they finally coalesce. These are dynamical horizons which merge and form a single horizon. But there are still errors. First of all, there is a truncation error that is common to all numerical simulations because this is a numerical evaluation. So of course you truncate at some stage in the numerical truncation. But second one is that the waveform is extracted at a large but finite radius. So you don't really, except in the Cauchy characteristic problem that I will mention in a minute, we don't go all the way to infinity to scry, but one just goes on a space like Cauchy surfaces, and one goes at a large radius. One goes at a very large radius, and this is something that is possible by the codes that are used by the Caltech Cornell SXS collaborations, stimulating extreme space-times collaboration. But nonetheless, it is extracted at a finite radius, and therefore they inherit error bars associated with the choice of extraction radius. The waveform is obtained by integrating twice with respect to the radiation field psi4, because we saw that sigma naught double dot is equal to psi4 naught. So I have to integrate this twice within time in order to get the waveform, sigma naught, which is the waveform. This requires introduction of coordinate systems because I need to know what is psi4 naught in sat psi4 naught double dot. And therefore, I have to introduce null tetrars also. And these become ambiguous if you are used at a finite distance rather than at scale. Finally, although one does have tools to calculate psi4, modulo the ambiguity is inherent in working at a finite radius, there are numerical errors due to high frequency oscillations in the psi4 because we are truncating, as I said, truncation errors. There are numerical errors in high frequency oscillations. But in order to, what one calculates is often just the first 4 YLM components, or if you like, the spin-weighted YLM components. So spin weight is 2, so typically it is Y minus 2 LM components. That is what sigma bar was, as we saw before. So that is what one is calculating actually. And therefore, since just L is just equal to 2, that means I'm really averaging out. And when I do averaging out just with YLM, rather than L equal to 1,000, L equal to a million, therefore these high frequency oscillations that will occur on the two sphere, they are suppressed if one calculates only the first few spin-weighted spherical harmonics because of the averaging involved. And therefore, only the most dominant modes are generally reported. So people don't report the full waveform. They only refer the spin-weighted spherical harmonics, y minus 2lm. So L equal to 2, L equal to 4, but one doesn't go to L equal to 10, for example, typically. It's really L equal to 2, L equal to 4, and various values of M in the YLM decomposition, in the angular smoothness that we're talking about. Now, the stitching procedure, which involves taking the post-Newtonian waveforms up here and stitching them with the numerical waveforms up here, that stitching procedure is inherently has several inherent errors. There are several sources of errors in the stitching procedure. First, the stitching procedure has several inherent ambiguities because it involves several choices. First, one has to decide the stage in the binary coalescence where one stitches the post-Newtonian and the numerical waveform. I mean, I'm going to get some numerical waveform here. This is certainly post-Newtonian, but do I start stitching here? Do I start stitching here? Do I start stitching here? So there's an issue there. And also the question is, do we do the stitching in the time domain, as I was showing just now, or in the frequency domain? Both these things are done, and there are advantages in going to the frequency domain. So therefore, there are choices to be made up here to create the final waveforms up here. Second, one must decide the post-Newtonian order and the T approximant to use in this waveform. And the third, the post-Newtonian and numerical waveforms are generally computed using different coordinate systems. These people use some coordinate system, these people use different coordinate systems, and one has to introduce additional inputs on a meaningful matching of these coordinate systems. And these choices are often driven by intuition. And again, I want to say that I admire the intuition that these people have really developed all the time. It works so well, and it is up to us, more mathematically minded people, to sort of understand, to provide explanation as to why it works so well. And so that is driven by intuition in the past experience, rather than clear-cut and ambiguous mathematical physics procedures. Next, because of post-Newtonian expansion and numerical simulations are based on quite different conceptual frameworks, there are several seemingly ad hoc elements involved. In the post-Newtonian calculation, the sources are taken to be point particles in Minkowski space. Now, this is an extremely important conceptual point that I think a lot of mathematical relativists are not completely aware of. The difference between the post-Newtonian methods and the numerical methods. In the post-Newtonian methods, there are these point particles which are moving in Minkowski space-time. In numerical relativity, there is no background Minkowski space, and black holes are represented not by point particles, but by dynamical horizons and neutron star with suitable fluid balls. In the case of black holes, the individual masses and spins in numerical simulation are determined by the horizon geometry, looking at the properties of the isolated horizon and the dynamical horizon, one calculates these masses and spins. So, whereas here, the masses and spins are associated with these point particles in post-Newtonian methods. Therefore, the stitching procedure, one starts with a control set of numerical initial data, for example, given by the Born-York data or Brand-Brugman data, that satisfies constraints in exact general relativity. Now, this data, we don't know if this data that I start out with is the correct initial data that would have been accumulated if I had started at minus infinity and evolved the system. So this initial data may have some spurious radiation, which escapes, however, the grid very quickly. And this is a fact that is very counterintuitive to mathematical relativists, but it's true. It does escape the grid very quickly. So this occurs. So you start with the numerical relativity data, you evolve it, but you ignore the first few cycles. First 3 cycles, say you ignore, because there's just junk radiation going out to infinity. You don't take that waveform seriously. You take the waveform after that seriously. So after this radiation has left, junk radiation, one reevaluates the source parameters in numerical solution, because we started with some data, but after the junk radiation has gone out, we can look at the horizon geometry and reevaluate the source parameters. And then one then identifies these source parameters with the post-Newtonian solution. One then chooses an interval in time or in the frequency domain. So again, a choice. Either you match in the time domain or in the frequency domain, and evolves both the post-Newtonian and the numerical solutions and compares their waveforms. There are several ways to measure the difference between the two waveforms, and one minimizes the difference by tweaking the time of matching, the interval over which one is matching is done, and the choice of the source parameters in the two systems. And when there is a match that is done, then one says, okay, so I matched it well now in this region. So to the past of the region, I'm going to use post-Newtonian. To the future of that region, I'm going to use the numerical relativity it is. And in between, I matched. But as you can see here, there's a lot of skill, there's a lot of intuition, there's an art and mixture of art and science that is involved in this teaching procedure. So conceptually, it is important to note that the matching is done only for the waveforms. For the two asymptotic forms of the metric, that is to say, that capture the radiative modes in the two schemes. So the matching is done by looking at just the waveform far away and looking at the two radiative modes, if you like, psi 4 naught or sigma naught or H plus and H cross of the wave. One is not trying to match the geometry interior at all. In fact, in the interior, there is no obvious correspondence at all between the post-Newtonian methods and the numerical solutions. Because post-Newtonian methods is Minkowski space, and there are point particles moving. There are no horizons. In numerical relativity, there are horizons. They're dynamical horizons, they merge, and so on and so forth. So there really is the interior of space-time for the post-Newtonian theory and for numerical solutions is completely different. The matching is done just for the waveform at infinity. In particular, there is no simple relation between the particle trajectories representing the black holes determined by the post-Newtonian equations and the dynamical horizons determined by the numerical solutions. So the post-Newtonian trajectories that you have learned about in these lectures, in this course, for example, their purpose is to just give us consistent waveforms that take into account radiation reaction and so on and so forth out at infinity. And one is only taking the waveform at infinity seriously, not the space-time that was used to produce that waveform. Okay. These considerations make it clear that even for the 1% of the waveform in the data form that are obtained just from post-Newtonian theory and numerical relativity, other waveforms are obtained by these additional inputs, as I was mentioning, by extrapolations and so on and so forth. Even for this 1% of the waveform, there is no systematic way to measure how well they agree with the predictions of exact general relativity. Inputs that go in the construction of the remaining 99% of the waveform are even less driven by fundamental considerations. To mathematical relativists, this can seem shocking. But it is important to note that similar phenomenological considerations and mixture of science and art are heavily used also in other areas of physics, such as QCD. There are phenomenological models, there are approximation methods, and so on and so forth, and not everything is derived from first principles. And this is what happens when you try to match fundamental theory with actual observations up here. And to me, it is a tribute to the physical intuition and the technical ingenuity behind the hybrid waveforms that the matched filtering procedure could lead to detection of binary coalescences. Okay, here is an illustrative list of examples of references. Again, this is far from incomplete, and you can see most of them are quite old. They only go to 2014, for example, or 15, not in the last many years. But I think that will give you the intuition for what is happening. So let me finish this lecture by talking about the two types of error that we have to worry about and what is happening. You might worry about, well, all these approximation methods are used, you produce these waveforms, and then you actually, use them to actually talk about detection and also about parameter estimation. Why can we trust all these things? So I think it's important to understand these two types of errors. The first is called systematic errors, and the second is called statistical errors. So systematic errors, these are associated with approximations or well-motivated tricks used in creating the waveform models. Shortcuts are inevitable because we want to cover an 8-dimensional parameter space, and computational speed is also important because, you know, anytime a signal comes in, one really has to one has to sweep through this bank of, you know, several 100,000 waveforms to see to find out the one with which the observations actually match well. And so speed is very important in generating these waveforms. More and more waveforms you want to generate, your procedure should actually be very, very, very fast. And therefore, these kind of approximation methods that are used, or well-motivated tricks that are used. So for example, in these methods, higher order LM modes are often ignored. So these things, as I mentioned before, are spin weight 2 harmonics, so Y2LM. So I'm taking, for example, I'm taking H plus naught minus IH naught cross and integrated against Y minus 2LM, and then integrating on two-dimensional sphere to obtain the waveform that we saw, because the waveform we saw was just one-dimensional in time, you know, and that was obtained by integrating this sphere, so that we are only left with U dependence on Scri. On Scri, we just have this U dependence, U up here, and theta phi dependence has been integrated out. So typically, one is just looking at lower LNM modes. Higher LM modes are often ignored, are not even listed, not even mentioned. Then fast and practical ways to accommodate the precision. You know, when we got the components of spin that are orthogonal to L are non-zero, then in fact this L actually is going to precess, and this precision has to be taken into account, and there are tricks to accommodate this rather than really fundamental principles. And there are ways in which inputs from numerical relativity are induced to fix some parameters which are unknown, undetermined in these waveforms. So there are such things that are done, and they give rise to these systematic errors. So systematic errors are errors coming from modeling in this waveform model. But then there are statistical errors, and they are associated with the fluctuations in the detector noise and necessary data analysis to extract signal from noise. Now, so far it turns out that the systematic errors, in spite of all these things that might seem surprising to you, the list of approximations and seemingly ad hoc elements that go into creation of these waveforms, these systematic errors are still smaller than the statistical errors. And hence the waveform models are adequate for detection and estimation of main parameters and test of general relativity so far, although the error bars could be reduced. But as we will see, as with future detectors, we are going to use, we really need more and more accurate waveforms. And this is not a view of just a mathematical relativist like me. This is the mainstream view of the LIGO Virgo community. Okay, so I should stop here, and I will talk next time. The follow-up lecture, the last lecture, I will show how you can use the balance laws that I had introduced as diagnostic tools for the waveforms to know if a given waveform is a good waveform, how much error it is, where it is bad in the parameter space, how you can improve it. So give such hints, suggestions to the waveform community coming from hard mathematical physics. Okay, I stop here, and I will take any questions if there are.
Yes, are there? Yeah, thank you. And are there questions before the break? Yeah, there's. Take one.
So thank you very much for the first half. I'm really impressed by the care that you take, the analysis. I really appreciate the discussion about technical aspects involved and the intuitions that people have in numerical community. But I wanted to ask, so the last time we were discussing possible technical issues when we were working with positive or negative cosmological constants in even defining radiation. So I was wondering, does it have important implications for things like holography? Maybe I'm completely mistaken, but we are working anti-de Sitter, right? So it could be relevant even for the holographic considerations. I don't know, maybe it's a stretch, but I was curious whether it actually, these ideas from failing to define it precisely could somehow impact the way we form theories in holography and string theory. Thank you.
Okay. So this is really has to do with the cosmological constant and particularly negative cosmological constant. Am I right? That your question really has to do with that?
Yes. So we were discussing the case of vanishing cosmological constant, and you were commenting about non-zero cosmological cases. So I was curious whether it could lead to some complications in holography.
Yeah, so this is not related, just for the audience, let me say. So this is not related directly to the way the waveform models and detection and so on that are discussed in this last lecture, this lecture that I've just finished. But it's a more conceptual question about the about lambda less than 0. This is what is used very heavily in string theory. In the real universe, the measurements show that lambda is positive. But because of supersymmetry considerations in string theory, one is naturally led to consider negative cosmological constant. And the question is about just I think you just want me to comment about this case and what we know and what we don't know and so on. So the statement is that there's a big difference between lambda less than 0 and lambda bigger than 0. In lambda bigger than 0, for example, in de Sitter space, we have got Scri plus is space-like. And these are cosmological horizons. Scri minus is space-like. And if you like, I mean, this could be, you can, okay. And whereas in lambda less than 0, Scri is time-like. There's no Scri plus Scri minus, which is Scri is just time-like. Now, it turns out that when it is space-like, I mean, I cannot put any boundary conditions here because, you know, the Cauchy data here is really completely arbitrary. I mean, if I restrict my Cauchy data, then I'm changing the system. But when Scri is time-like, as in lambda equal to 0 case, and if you give me a Cauchy surface sigma up here, so here, if you give me a Cauchy surface, I can evolve all the way to if you give me a Cauchy surface like that, I can evolve all the way to Scri plus and evolve back all the way to Scri minus up here. And in fact, Helmut Friedrich has shown that when Scri has when Scri has a S3 topology, he has shown that in fact you can give yourself Cauchy data here, and for small Cauchy data in the nonlinear sense, I can actually evolve all the way up to Scri plus. But in this case, I got space-like surface, and therefore, really the Cauchy problem is not well posed. I need boundary conditions at this thing. So we need boundary conditions and Scri in order to talk about the Cauchy evolution of it. And the first boundary condition that can be used, and this is something that I discussed long time ago, is that the magnetic part of the Y tensor defined by this space-like normal on Scri equal to 0. And this is often used, is called reflection boundary condition. And then, you know, we also discuss, this can be done also in higher dimensions. This kind of boundary, generalization of this boundary condition can be done also in higher dimensions. It's a paper that I wrote with Saurya Das. Okay, higher dimensions. So in this case, the statement is that I really had a conceptual problem of actually giving them some boundary condition. And I can give myself, for example, this boundary condition. If I give myself this boundary condition, then that immediately implies that the group of symmetries is anti-de Sitter group. In other words, the diff Scri reduces to just the anti-de Sitter group. and then we can define energy, etc. But this means that there is no radiation which is actually going across Cry. It's basically a reflecting boundary condition. It says that if some waves come in, they are just reflected back. And this is perfectly consistent to do it. But the point is that in lambda less than 0 case, you need some boundary conditions in order to make the Cauchy problem well posed. And if you choose suitable boundary conditions, then there are no, I mean, for example, in particular, if you choose this, then there are no certainties. I cannot choose BA equal to 0 boundary condition, because if I did that, then in fact, there is no radiation, as I was saying before, or as somebody in the audience had pointed out, you can use a criteria of the Bell-Robinson tensor, and then you'll see that there is no radiation here. So this boundary condition is something for Scry I cannot use. For Scry at lambda bigger than 0 case, I cannot use. But for this case, I can actually use such a boundary condition, and there'll be no problem. So I don't think that there is tremendous subtleties involved here. Of course, there are subtleties involved in understanding the meaning of these boundary conditions, the physical appropriateness of one boundary condition versus another, the differences of predictions with different boundary conditions, that you have to understand. But there is no fundamental problem associated with these boundary conditions in the anti-de Sitter space.
Are there more questions before the break?
Hi.
Hello.
So my question is related to this one, to the cosmological constant. So on the one hand, observations are telling us that the cosmological constant is positive. The theory, as you have explained to us, is telling us that there are fundamental differences with respect to the asymptotically flat scenario. And on the other hand, I have the feeling that each time I read about approximation methods or gravitational wave phenomenology, even memory effects, no one talks about the positiveness of the cosmological constant. So I find that this is kind of paradox, and I would like to know your viewpoints on this matter, or correct me if I'm wrong. Or how can we convince these people to pay attention to this problem too, from the observational point of view? Thank you.
Very good question. So what happens is the following, that as I was mentioning before, so if these questions are discussed in detail in a paper in which two former students of mine and I did quadruple moment the quadruple formula. So let me just give you this reference up here and then explain and then answer the questions. So quadruple formula for lambda bigger than 0 case. So this discusses the questions that you asked, namely, why can we ignore the cosmological constant in these considerations, that when people are looking at the LIGO and pretty soon also LISA. Okay, good. So the thing is that the following. So supposing I got some quadruple moment which is changing now in de Sitter space, lambda bigger than 0. So here is a source that is changing up here, binary, say for example, and it's going to be radiating energy up here. And then there is a host of problems that are a priori seems completely different from this situation and the situation in which we got lambda big equal to 0 situation. But in fact, I don't want to go into the whole detail because really you can see this. So this paper is with Beatrice Bonga and Aruna Keshavan. There's a physical review letter, but there's also a physical review paper. And I ask you to look at the physical review paper where very detailed discussion is given of these issues. Okay. So briefly, basically what happens is the following, that we can ignore you're right, there is a cosmological constant, but we also know its value, and it's extremely small. And so basically the systems we are looking at are so far within our cosmological horizon. So if you like, if the system is here, we are somewhere here. And we are receiving this gravitational radiation up here. So it turns out that for this kind of situations, I mean, they're still very far, but they're still well within the cosmological radius. And then therefore, for these systems, we could actually use these cosmological horizons as approximate sky plus and sky minus. We can also use sky plus here by itself as sky plus, and you can actually calculate what happens with the quadruple moment formula, and you do find, exactly as you say, corrections to the quadruple moment formula. But those corrections are completely, absolutely negligible because they involve basically the cosmological constant, if you like, or the value of the cosmological ratio of the value of the cosmological constant. The value of, say, for example, the wavelength of the radiation that is radiated divided by the cosmological constant. And this is completely negligible here. And therefore, in fact, even at Scry or here, if you actually calculate with the cosmological constant, this is only quadruple formula, so this is only the linearized series, so it's not full general relativity. But still, if you calculate that, you find that there are corrections that have been explicitly evaluated here, but these corrections are absolutely small for this. Now, when it comes to what now is being discussed, which is really very, very early universe and supermassive black holes, which are circulating and which are coalescing, that they have been there for forever. Now, unfortunately, the signals that they give us seems to be creating a background rather than a clean signal from a given isolated system. There are many, many of them, and what one gets is just background. This is something that was announced just in earlier this month, in fact, in July. So by the pulsar array observations up here. So for them, the statement is that if you could, at the future detections, if we could actually get signals from the supermassive black holes, which are found very early on, and therefore their wavelengths, they're very far from each other, their wavelengths are very large, and that kind of, their ratio of that compared to the cosmological radius is not completely negligible, is not. So that for those systems, it will be the case that the correction terms that I'm talking about will be very important. But for what LIGO is going to see with advanced LIGO, what Cosmic Explorer will see, or Einstein Telescope will see, these corrections, these conceptual problems associated with the cosmological constant don't really matter. Those are deep conceptual problems, but in the sense of practical contributions that they will actually provide are very, very small. We do have to take into account the redshift, because how far the object is, so their wavelength is going to not be the same as the wavelength at emission. We have to take into account. But apart from that, other effects are very, very negligible. So I think this is important for theoretical people to really work this out. After all, Bondi and all these people worked out this case. In the 1960s, so it was 60 years ago, and now it is people completely ignored it forever. Now it is in the center of attention. People are actually using this framework. So similarly, what you do now would be in the center of attention in future with lambda bigger than 0, but not in the next 10 years or 20 years. It will be more like 40 years from now. So that is where we are. Okay, maybe we should stop and we can come back. And if there are further questions, I'll be very happy to answer, because I can adjust my last talk depending on how many other questions there are.
Very briefly, sorry. Very briefly.
Sorry, I will be very brief. So the argument that you give is, as I have understood, is based on this quadruple formula, but this is the linear regime. So what is telling us that behind the horizon, after radiation crosses the cosmological horizon, nonlinearities would affect the signal that one eventually would detect at the sky?
No, I think that what happens between here, you're right. I mean, one has to show this explicitly, but I think one has a lot of intuition about what happens, and so one uses.
Intuition is fine, but one has to
No. But what happens between here and here is all that.
Indeed, you can have
curvature is completely
coming
negligible.
from another part of the space-time, right?
Yeah, but curvature is completely negligible here. That it's not going to affect. I mean, we have calculated, right? We have calculated what happens here
in the linear
for the linear case, but for the non-linear case, I mean, work is in progress. We will be able to calculate here. I mean, I'm not giving you all the answers because, in fact, a lot of work is in progress with Jurek and Maciek Kalinowski about really defining radiation fluxes formulae here in a full non-linear regime. It's not complete, but it's close. So I'm giving you from the intuition that I had from the nonlinear regime. Published work is all in the linear regime. This nonlinear regime is not really published so far. So I still want to insist that, I do want to insist that, in fact, these are conceptually very important questions because we do need to understand what we mean by radiation, not just the criteria if there is radiation, but really the flux formulae and energy and momentum, balance laws, and so on and so forth. We need to understand. We need to understand the difference between here and here in the full nonlinear regime. But I do think that this will be understood. But I encourage people to think about these things very much.
Okay, thank you for your answers.
Yeah, right. But the statement is that I don't expect, even though I myself am working on this quite a lot. I've been working it for last 6 years now. But I think that our contributions are not going to be significant for advanced LIGO or Einstein telescope or terrestrial instruments in the next 10 years.
Okay, are there more questions? If not, let us make a break, 10 minutes break.
Okay. Okay. Can you hear me, please?
Yes.
Okay. So, but now we'll sort of, last lecture was a major detour because I had to familiarize you with what the techniques are, what the ideas are that go into the creation of these waveforms, and why it is important to check if the waveforms are actually accurate, because there are so many inputs that go in which don't follow from fundamental considerations. Okay, so now what this last lecture, I would like to return to the main thing that we've been talking about, the mathematical structure at SCRI, the conceptual and foundations at SCRI, which gave us some balance laws, and we want to use them as a diagnostic tool to check the waveform models. So these waveforms from the effective one-body approximation, phenom models, and surrogate models have proved to be invaluable for the impressive detection of the compact binary covalences through gravitational waves. But we are now entering an era of abundant rates. In fact, very soon, in the next LIGO run, we'll have as many as 1,000 black hole, could have as many as 1,000 black hole mergers a year with masses less than or approximately equal to 100 solar masses. And with the LISA and third generation detectors, Cosmic Explorer and Einstein telescope, we will achieve a much greater sensitivity or significantly larger frequency band. And therefore, for accurate parameter estimation and tests of general relativity, one needs quantitative measures of the accuracy of the waveforms relative to the exact one. So the key problem here is that we don't know what the exact general relativity waveform is. If we knew what the exact general relativity waveform is, then we could just compare the waveform model with this form and see how accurate it is, or where it is bad in the parameter space and so on. But we don't know the exact GR, and therefore in the literature, accuracy tests involve comparing the waveforms with numerical relativity. But there are big regions in the parameter space where the numerical simulations are sparse or almost absent, and so direct comparison is not possible. Also, numerical results themselves have some errors because of extraction at finite distances, extraction of waveform at finite distances, the truncation errors, and the absence of, or so far, absence of higher harmonic waveforms, and so on. And so balanced law provide an alternate rule to complement numerical relativity. And they can be used anywhere in the parameter space and can be used to test numerical relativity itself. And the key feature is that these balanced law provide us an infinite number of constraints on the waveform without having to know what the waveform is. So if you give me a waveform and say that here is my good approximation to the waveform, I will be able to test. So whatever the exact waveform is, it must satisfy the supermomentum and angular momentum balance laws. I put angular momentum in small letters because we have not really discussed them. Therefore, given any candidate waveforms, its violation of these constraints provides an objective measure of how far it is from exact general relativity without the need of comparison with the unknown exact waveform. So this is the idea, and I want to give you some examples. I know that most of you are not into approximation methods or waveform models and so on and so forth. So I just chosen 3 or 4 examples. There are many more in the references that I gave you, that I'm giving you. So here is a picture that we have in mind. We got some compact binary coalescences. It coalesces here. And you have got the waveform here. For a long time, the waveform is just the spiral phase. And then here we have got the merger phase. Just a second. And then we have got this quasi-normal ringing phase up here. So that is what is symbolically being told up here. And what we want to know, the balance laws tell us, is it basically that there is a supermomentum charge integral up here. There is a supermomentum charge integral here. And the difference is given by the flux up here. And there are infinitely many such balance laws because there are infinitely many supermomentum generators. So F is a conformally weighted function. And it says that Fn at u equal to, so I'm looking at the total balance law, Fn at u equal to minus infinity, and then what the flux is what the charge is at minus infinity, what the charge is at plus infinity, and is equal to the flux across all of Scri. People have also looked at, in fact, for finite regions of Scri, and they use that. I'll mention that in a minute. And now the charge is just given by integral on a 2-sphere of the weighting function of the supertranslation, conformally weighted function up here, times the real part of psi 2 plus sigma bar dot. Now at minus infinity and plus infinity, this term disappears because sigma dot goes like 1 upon u to the 1 plus epsilon. So therefore, sigma dot actually is going to 0. So this term isn't here. And so I'm just left with psi 2 up here. So I'm looking at the integral of psi 2 in this past limit and integral of psi 2 in the future limit. And I can evaluate it in any conformal frame. And typically, one often uses just the Bondi frame, a given Bondi frame up here. And then the flux is given by integral on all of Scri. The flux is given by integral on all of Scri up here of so this is a 3-dimensional integral. This is d2s, if you like. This is a 2-dimensional thing. Maybe I should just correct it right away. And then du, and then du, the integral on the generator, and then I got here nu squared, and then h squared of nu up here. So this is quadratic in nu, as I have told you last time, and this is linear in nu in the terminology that is often used in celestial mechanics or celestial holography. And this is the soft term, and this is the hard term. Now, since f is arbitrary, we can peel it off. So that is really remove this two surface integral because f is arbitrary, and therefore I will get here an equality if I peel this f off for arbitrary f between the charges, namely psi 2 at u equal to minus infinity and u equal to infinity, and the flux. And the flux, again, I've integrated out, I removed this, remove the S2 integral. I removed the S2 integral up here. And so I just get integral minus infinity to infinity. Basically, I remove these two things. So I get integral minus infinity to infinity of nu squared and then h squared of nu's. Now, we're going to see this in some detail, but this is something that actually is just provided for me from the waveform model, because waveform model gives me sigma naught, and therefore I can just calculate sigma naught dot and I'll calculate this object. So any given waveform model for some initial parameters of the binary system will actually be able to give me this. And we will see in a minute that this also is determined by the data that is given to me by the waveform model. Namely, the data is really the initial and final masses and the kick velocity. And the kick velocity is because I can be in the center of mass frame, and therefore in the distant past up here, the 3 momentum is 0. I only have energy. But the radiation goes out through sky, and this radiation can carry away linear momentum. And as a result of which, the final black hole related to the center of mass frame has a big kick. I mean, typically this kick is as big as 100 kilometers per second, but people have sort of seen simulations in which there are even 1,000 kilometers per second. So one can actually calculate this kick velocity, and we'll talk about this in a minute. But the basic thing is that this is something that the waveform model gives me, and this is also something that is provided to me by the waveform model. But they are provided independently, and therefore I can just see if in fact this quantity is equal to this quantity or it is not equal to this quantity. And since this is a function of theta and phi on both sides, since I peeled off f and the two surface integrals, I get infinitely many conditions between what psi 2 does at minus infinity and plus infinity, the difference, and the flux across chi provided to me by the waveform model. And any candidate waveform model must satisfy these infinitely many constraints to the desired accuracy. Let us now consider the simplest constraint. So here f was arbitrary, or if you like, this theta phi is arbitrary. And let us just choose for f here the first 4 YLMs. Or to begin with, even put f equal to 1. That is to say, we're just looking at the mass in the case, the energy in the case. So just look at translations is what I'm saying. And when we do that, so we just look at the translations, the first 4 YLMs, and therefore we're going to 4 momentum balance law. So first of all, we can just look at y00. And y00 already tells us something about the accuracy of the waveform. And here is the example that I gave that we examined in great detail. We examined the very first LIGO event up here that was given to us. And what we did was just look at here, if you like, the integral of this, that is the y integral against y00, which is just constant, and also integral of this quantity. And so we want to compare the two quantities up here. And so this is something that is given to you. So, so we looked at simulations in which the initial parameters are the same. So the initial parameters at u equal to minus infinity is the same. So we can just look at the final parameters. So this parameter is the same for the various waveform models. Therefore, the final parameter will depend on whatever the waveform model gives us up here. And so we can just look at, calculate those. So here is a phenom model, and here is the EOB model. So what we do is we find that this is the very first event, the most well-known event. And then what we find is that for the phenom model, I get a nice nice curve like that. Whereas for the EOB model, I get a double hump. Now, of course, these things are, if I look at the scale up here, the scale is such that the difference between them is still within the systematic errors, but still there is a difference up here. And then these are the probability up, the posterior probability distribution for the inferred observable, which is M plus. So the M plus, which is really what is happening at u equal to minus infinity, is an inferred observable, because given the waveform and given the input parameters of what is happening up here, given the waveform, I can calculate it, and therefore I can infer the observable up here. And what we've done is, what the numerical relativity, which is really the surrogate, is really using the numerical relativity. What the prediction is from numerical relativity, if you like, using the law that we just talked about, and what given the initial parameters, what the numerical relativity will tell you will be the final parameters. These are in red and brown. And then we got here in blue and green the predictions of the phenom and predictions of the EOB up here. And we find that there is a difference between the two. But it's not so much that there is difference, but here there is a double hump. And the question is, what is the origin of this double hump? So clearly there's something wrong with this model. I mean, a small error, but still it can be improved. And so the question is, what is the, so this signal, the need to re-examine, and this was traced back to the way that the UOB model treats precession. Remember, precession is that if the two spins are not aligned or anti-aligned to the orbital angular momentum, then the orbital angular momentum precesses. And the way that the precession is treated in the UOB model actually produced, so these are really the spin vectors, if you like. So it really also produced a double hump in UOB. Whereas in the phenom model, this particular observable, which is talking about precession, is really peaked, just sharply peaked at one point, whereas here it is peaked at 2 points up here. And this double hump really carries over to this double hump here. And so it really, this Balanced law provided guidance about how to improve the EOB model up here. And in fact, the improved models have been done, and then the improved model of EOB looks much more like the model that I got here for the phenom. There's a second example in which, in fact, both models don't do very well, and phenom does even slightly worse, which has to do with the posterior probability of the kick velocity. So, as I mentioned before, what we have up here is that initially we can be at rest. We can go to the center of mass frame, so the three momentum is actually 0, but the gravitational radiation goes through scry, and then for the final three momentum in the initial rest frame is not 0, and that is given by the flux of the three momentum up here. So we can calculate that. So this is the second example. We can calculate how much radiation, how much three momentum radiated away, and it is just this. And this then three momentum radiated away is given by the Lorentz factor times the final mass, because this is the momentum imparted to the final mass, times the velocity of the remnant up here. So we can calculate the kick velocity by this formula. Take this thing and calculate the kick velocity. And they were all over the place, basically. So in the phenom model, the kick velocity was extremely small. In the EOB model, it is much larger, but still small. And in the if I do fit to the numerical relativity for the parameters which are given to me by EOB and phenom, then in fact for numerical relativity, the kick velocity is larger. I mean, larger than both of them, much larger than this one, but also larger than that. And so the Balanced law is really badly violated in both models, much worse in phenom than in the EOB case. And diagnostics here, we found out that the phenomenon is funny because the mass was perfectly fine, but or the energy flag was perfectly fine, but the 3 momentum is very bad. And the reason is because what contributes to this 3 momentum, I got here sine theta cos phi. In the case of mass, I just have one, is really higher order modes, which are in sigma. And these higher order modes were not treated well by the phenom model. And once they were actually, these effects have been incorporated, and again, things have been improved. So these are very simple examples, the simplest possible examples of the balance law. The balance law is really, we got infinitely many of them. And what we did here was to just choose f equal to alpha, namely the first 4 YLMs, alpha naught, Y00, plus alpha m, Y1m. And then for that f, we looked at the balance law, and we found that the models could be improved even for this very first event, which has been so well analyzed. And then, of course, now models have been improved in this particular way. Now, what about higher boards, L bigger than equal to 0? Because here I just looked at L equal to 0 and L equal to 1. What about L equal to 2 and bigger than? So now here, I just want to explain what happens up here. Now, the usual assumption that is made in the compact binary coalescence analysis is that, as I said before, the news function dies as faster than 1 upon u, so that the total energy radiated away and angular momentum radiated away is finite. And then the system is asymptotically stationary. I mentioned that before, that all these models, post-Newtonian models, assume that the system is stationary in the distant past. In the distant future, it is approaching curved space-time, so it is stationary. But of course, the past rest frame may not be the same as the future rest frame, as we just saw, because of the kick velocity and so on. So this is something that is perfectly okay, but the assumption that at u equal to minus infinity, the usual post-Newtonian assumption that the system is actually can be taken to be stationary is quite strong. But this can be weakened. Namely, we keep this assumption because we will know that the total energy and angular momentum radiated away is finite. And then what this assumption says is really that the Lie derivative of KAB is equal to 0. That is to say, it tells us that, and also the same thing with star KAB. And so that is to say, it tells us that psi4 and psi3 are dying. That's not very surprising because news is dying. So psi4 and psi3 are going to 0 at the two ends. And psi2 dot is also going to 0 at two ends. So this is the information that I get by just assuming that the news is dying up here. So I'll obtain that psi2 dot is also going to 0. So we make an additional assumption. We replace 2 by another assumption, which is much weaker, which says that psi1 not dot also goes to 0. Here one says that psi1 dot is just 0 before some time. And here we're saying that it only goes to 0 asymptotically as u go to plus minus infinity. At u equal to plus infinity, it does go to 0 because there's a curved space-time. But at minus infinity, this is an assumption that we're making, that the system is such that asymptotically psi1 dot goes to 0. In this sense, it is asymptotically stationary rather than stationary before some time. But it's also very weaker because we're not making any statement about psi 0 and so on and so forth. Whereas here, psi 0 would also be asymptotically, would also be 0. Psi 0 dot would also be 0 before this particular time. Now, this has an interesting consequence. Namely, if I go to the Bondi frame in which the 3 momentum vanishes in the future or in the past, then psi2 naught is real and spherically symmetric in the past. And if I go to the Bondi frame in which the 3 momentum vanishes in the future, then psi2 naught in that frame in the future is also spherically real and spherically symmetric. However, in general, the past and the future rest frames are different because of this kick that gravitational wave carry away 3 momentum. And typical numerical simulations, we get a few 100 kilometers per second kick up here. So suppose the 3 momentum carried away is carried away in the x direction. So this is the 3 momentum that is carried away in the x direction. So again, Lorentz factor, the final mass times the velocity. So this tells us what the velocity is, because the waveform will tell me what this is, and this will tell me what the waveform will be. So we can now work in one body frame. So typically one works with a rest frame that is adapted to u equal to minus infinity to I naught in the distant past. So in this rest frame is the center of mass frame, if you like. Then psi 2 naught here is spherically symmetric, and therefore it is just given by G times M naught. It is spherically symmetric. In the future, psi 2 naught is spherically symmetric in the future rest frame. But if I look at the past rest frame, because I want to use the same Bondi frame, both in the past and the future. So if I look at the Bondi frame, which is adapted to the past rest frame, then psi 2 naught is not the same, is not constant, but it's a given. So in the future frame, it will just be G times M at I plus. But now I get a Lorentz factor. You can just work it out, and you get this answer up here. And therefore, if I take the difference between psi 2 naught at the two ends, right? If I take the difference between psi 2 naught at the two ends, maybe I should just leave it as it is. Okay. If I take the difference between psi 2 naught at the two ends up here, then that is completely determined by M naught plus up here, and the kick velocity. And the kick velocities can be derived from the waveform up here. And therefore, I get an equation which says that I'm just looking at the balance law. The balance law will just say that this psi 2 naught, so psi 2 naught, the difference between psi 2 naught is given by this flux integral up here. So I'm just using that balance law now. And that balance law just tells me that psi 2 naught at plus or minus infinity, which is as a difference between between M I naught and this quantity up here. That is a difference between the two. I'm calculating everything in the past bond in the body frame in which the system is at rest in the past, and therefore this is just given by something that is given by the waveform model. And this can be computed for each form in the waveform in the catalog. And the question is, how well does a given labeled waveform satisfy them? So waveform is labeled by the parameters mg and m naught by this individual masses up here, and so the spins of the particles of the two black holes. And so how much is it? How well does it satisfy this balance law? And the statement is that one can decompose the waveform into the this was L up here, so let me just say that. I don't know why this is always this is L up here, so let me just say this is L, the YLM. So we can decompose the waveform into the YLMs and obtain a constraint for each LM. We already discussed L equal to 0 and 1. And now for L equal to 2, the dominant modes are plus or minus 2. And the waveform models and in numerical relativity, one aims for great accuracy for this. But it turned out that in the SXX catalog, the waveform model catalog that we got in numerical relativity, the stimulating extreme space-time catalog, Caltech Cornell catalog, the L equal to 2, M equal to 0 mode was poorly represented until recently. And the source of errors believed to be associated with the extraction at large but finite radius. The radius is large because one uses spectral methods. So one can go to 1000 M, for example, to extract the waveform, but still it is finite radius. And then you can do this Cauchy characteristic evolution, which gives us, in other words, you go to a particular 1000 M using Cauchy evolution, and from 1000 M, you use a null cone to evaluate, and that is a characteristic evolution. So, but these are very expensive numerically, so you cannot do it for every waveform, but just a few waveforms one can do it. So using this, that gave accurate results because they extract the waveform at scry, and therefore, for them, M equal to 0 mode was perfectly fine. But this method is extremely slow. So Kera and the SXX collaboration use the finite time version of this balanced law that I just wrote down up here in order to calculate the L equal to 2, M equal to 0 mode of the waveform and updated the SXX catalog in 2021. So this balance law was concretely used in numerical relativity to improve the waveform model, particularly for the L equal to 0, L equal to 2 and M equal to 0 mode. And in the second paper, the same people improved the recoil velocity in the SXX catalog, again, because the higher modes were not properly treated. And so the balance law showed them how to correct it, and that has been corrected. And the last example I want to give is the following. That let's look at even further higher modes, bigger than L equal to 2, for example. Then what we can do is we can calculate what is called as gravitational memory. Now, normally you will see in books and such in our papers saying that, well, gravitational memory has not been measured. It is true, it has not been directly measured, but neither has the final mass of the black hole or the final spin of the black hole directly measured. But they are reported in every LIGO paper. So what are they? Well, I like the terminology that these are what one would like to call as inferred observables. In other words, you give a waveform, and the waveform is labeled by incoming parameters of the binary. You obtain the best fit using whatever waveform model you have got, and that waveform model then evaluates what the masses and spin are at the end, at the very end, and also tells us, the numerical evolution tells us what cycle naught is at the end. And therefore, actually, I can calculate the gravitational memory because I got the numerical model is giving me the news all over the place. And therefore, using the news, I can calculate the integral of the news along U is going to give me the gravitational memory. And this can be used as an inferred operator. And conceptually, it is the same as the final mass and the final spin of the black hole as an inferred observable. And they can be obtained by just rewriting the balance law. The balance law was written as saying that, psi 2 naught at plus minus is given by this. So we just rewrite it as follows. We just say that, well, I want to know what is the change in sigma or in the waveform model. So I take this term, and I got here d by du. Therefore, I can just integrate out this term d by du, and I will just get h squared of sigma up here. And I move this term to the left-hand side, and I will get h squared of sigma at u equal to plus infinity and u equal to minus infinity, h squared of sigma at u equal to plus infinity, minus infinity, and u equal to plus infinity. This difference between h squared of sigma is exactly the memory up here. So I can calculate the memory by taking this on the left-hand side. Waveform model gives me this, waveform model gives me this. So I can just calculate that. So that is what is done up here. This is just a numerical constant. This is the change in h. H is the same as sigma. So this is the change in sigma in going from u equal to minus infinity to plus infinity. And that is equal to, I moved this term, and then I moved this term to the left-hand side. So therefore, first of all, I get the term which was on the left-hand side, and this is the second term that is moved on the left-hand side. And this dl is the luminosity distance. So actually, we can calculate what the change in HLM is. And this is really the memory. The change in the H or change in sigma in going from minus infinity to plus infinity. And again, it is plotted for the three models, phenom and EOB, for different LM. So this is H20, H21, and H40. And you can see that for H20, there's very good agreement. As we go to the higher modes, the agreement becomes not so good. And in particular, phenom model here, the agreement, the shape is very strange, and you sort of feel that somehow the observable is not being well measured here. And this waveform model gives statistically different values of this observable. So they cannot both be good approximations to the exact waveform model. At least one of them is wrong. Maybe both of them are wrong, and are wrong in the sense that are not accurate enough. And near the parameter values corresponding to this particular event that we have, one or the both waveform models need improvement or higher modes. And then this is the way in which balance laws inform the waveform community where something is not right and that needs to be improved. And then finally, I just want to stop here really, but I included some slides about angular momentum, and you can go through them yourself. They start from here. It's the same idea. The angular momentum balance law also gives us, tells us about limitations of waveform models, and they can be improved. So this is sketchy, and I just leave it for you to go through that. So let me just summarize here. For the course as a whole, it is interesting to note that the 6 lectures covered a very broad spectrum of ideas that have been developed over 5 decades. The constructions and techniques developed in the 70s and 80s still provide the foundation for all the forefront theoretical work in gravitational waves. They involve an unforeseen and beautiful interplay between geometry and physics. We saw that in the last 2 lectures, this lecture and today's lecture, earlier one, that in addition, the older ideas have a down-to-earth practical application as a diagnostic tool to probe the strengths and weaknesses of waveform models vis-a-vis exact general relativity. And we don't know what the waveform model is in exact general relativity, but we can still use these identities, which are valid exactly in the full nonlinear general relativity, to test how various waveform models are performing. And where in parameter space they are not performing well, and you can pinpoint that and then give some directions to improve them. They can also serve to bring out the limitations of the numerical simulations themselves vis-a-vis in general relativity and improve them. We saw some examples for the memory, and angular momentum is another example. In fact, one of the items in the SXCat catalog, the angular momentum balance law is extremely badly violated. So we pointed that out, and they corrected that. There was just a mistake somewhere in the programming, and this is discussed in the slides that I in closing, but I'm not going to go through. So even the numerical relativity waveforms have been informed by these balance laws. Okay, now this is the key point. This is possible because each balance law enables us to examine the accuracy of the waveform through the lens of a specific observable of exact general relativity. If you just look at the waveform, you don't know where it is accurate. But if I want to say, give me this waveform, and I'm going to test how well it does with respect to the supermomentum balance law for L equal to 3, M equal to -3, then I got a specific observables, I can see how well it does. It may not do so well, and then I can suggest how to fix that thing. So it's because we got infinitely many observables, the supermomentum and angular momentum, and each of balance law gives us a lens through which we can examine a given waveform and judge its accuracy. This accentuates strengths and limitations of waveforms that are otherwise not apparent, because it's a usual thing, right? I mean, you look at it through a filter, through a lens of a given observable. We do that on quantum mechanics all the time. If you have got a wave function, and that may be very well to calculate energy, but it may be horrible to calculate angular momentum, for example. And then we improve that wave function. So the same thing is what is being done here. So I want to stop here, and if there are any questions, I will take them, either about this topic or anything that we discussed in the course. Hello, are you there?
Let me ask the first question. Okay. So there are infinitely many super translations, but for the angular momentum, there are only few generators. So we don't have that many balance laws. Is that right?
Right. I mean, it depends on what you mean by angular momentum, right? I mean, yeah, you're right. So if you count, I mean, the point is that you give me one generator of angular momentum, I can add it to a super momentum, and that gives me another generator of angular momentum.
Right. So the difference is super translation, which is
right, different super translation. So if you already have counted super translations, then you're only left with 6. That's correct.
Oh, okay, thank you. Are there other questions?
Okay, maybe it's completely non-concrete, but we had previous lectures about the gravitational waves, and the self was free from Adam Pound, and he was discussing how the new advances in analytic and numerical methods would possibly constrain parameters, for example, for quantum theories of gravity to a large degree. So I'm working in this direction. So I was curious to get your opinion about how optimistic can we be about constraining possible models for quantum gravity for some from gravitational waves observations and coalesce of black holes.
Okay, so already, in fact, they have constrained some models, right? I mean, those of you who are more in quantum gravity and so on might remember that a while ago there was a lot of interest, a lot of thinking that, in fact, with the firewalls and then subsequent developments inspired by string theory, there was a lot of speculation that even for astrophysical macroscopic black holes, the structure near the horizon would be quite different because of quantum effects. The structure of the horizon would be quite different from that of general relativity. And we got about more than 100 LIGO events, and we see none of that. And so if you like, we're already constrained. We're said that no, general relativity is perfectly fine. For astrophysical black holes, the horizon structure is perfectly fine. There's no problem at all. So if you like, we're already constrained things that some of the models that people had put forward for quantum effects of gravity and using gravitational waves, those ideas that classical gravity would be violated even in tame regimes where semi-classical approximation should be valid, that idea, I think, is pretty much out of the window now. Now one can be more ambitious and try to put more, say, further constraints. There are these ideas about echoes and so on and so forth. Now, I like Jurek and other people in the room there, I work in loop quantum gravity, and from the perspective of loop quantum gravity, the effects for macroscopic black holes, solar mass or more than solar mass black holes of quantum gravity would, of course, there are effects. There's no question about it. Of course, it's just like, quantum mechanics is important. There are quantum effects for the motion of the moon around the Earth. There's no question there are quantum effects, but they're completely negligibly small, and so we don't bother about them. So there are clearly effects of quantum gravity, even for astrophysical black holes. But in my view, and most people working loop quantum gravity view, for astrophysical black holes, these effects are going to be extremely small. But this is because we're looking at quantum gravity problem from certain perspective. I would personally be very surprised if, in fact, gravitational waves lead to some discovery which tells us about how classical general relativity has to be modified by quantum gravity effects. So I would be very surprised if something like this comes out of gravitational wave observations of astrophysical black holes. If you like, the success to date is precisely saying that no, the quantum effects are not important at this level. In the sense that those models which suggested that quantum gravity effects would be important even at the horizon and outside the horizon of macroscopic black holes, those have been ruled out. So did I answer your question?
Does it mean the end of the firewall era, or is it too much?
Oh yeah, I don't think anybody will. In my view,
Thank you.
What I know about it, nobody believes in firewalls anymore. I don't think. Yeah.
Okay, I have a question regarding this improvement of models. So
Good.
you stated that we can check these what is it, conservation laws, balance laws, and then use them to to check whether like they're violated and then maybe improve the models. Well, now is this statement like does it carry this artistic meaning that we have to think about something smarter just in some general way, or is there some like a surgically precise way to improve the model? For example, that we calculate several balance laws, so we see that we have a number of violations, some are larger, some are smaller. So is there a way to use this very precisely, to use it to improve the models in a very precise way, or is just really we just have to do something better, but that's it?
Very good. So it's not surgical. It doesn't tell you this is exactly what is wrong. But on the other hand, it is kind of semi-surgical in the sense that it tells you which region in the parameter space you use, your model needs to be improved. I mean, I already gave this example, right? I mean, for example, in the case of in the case of even the famous event, the first event up here, even in that case, the EOB model, which was used for this event, its predictions for the mass were, and if you look at the Balance law, its predictions have this double hump, and there's something clearly wrong, and then we could trace that double hump back to the way that the precision was done. Now, this involves a whole bunch of steps which involve understanding of the model a little bit better as to why could it be wrong or something like that. And then we pinned it down to the precision being incorrect up here. And then, but as I said, the model has been improved, and now the new improved model doesn't have this double hump. Similarly here, for the phenom model for this kick velocity, it's clearly something is wrong. 10 to the 5, 10 to the 5. This is 10 to the minus 5, 10 to the minus 16, and the fit up here is in fact 10 to the minus 1. Let's see, 10 to the minus 3. So there's clearly something wrong here. And again, we could say that, well, since, for example, the phenom model was perfectly fine for the mass, so y00, but it is not good for for the momentum. This involve the y11, if you like, and then this involve up here. That means that this product up here, it must be wrong with respect to what is happening in the higher modes that appear up here, and therefore the improvement had to be with the higher modes, and that is exactly the diagnostic that was done, and it is higher mode. So I don't want to say that, well, this just tells you that the model is incorrect for some parameter space, and then you just don't say anything. You do give them hints, but it's not surgical. It's not saying that, well, you go and do this. You have to look at it case by case, and then case by case you can tell, like here, that in fact something is wrong with the higher morals, something is wrong there. For the SX, now this is numerical relativity, not a model, but we could pinpoint that in fact we could pinpoint that we could pinpoint that in fact L equal to 0, M equal to 0 mode that they themselves are already worried about before is really badly treated, and using the Balance law you can fix it. So it provides some. In this case, they already knew that there's something not right about this. But Balance laws then provided a way. First of all, confirm that there is something not right about it, and then provided a way to fix it. And finally, there are things like in the case of I just don't. If I can quickly find it for the angular momentum balance law. Similarly, if I can find, this is some events from the not LIGO events, but the simulations from the SXX catalog, and then you can see that here there is some quantity which is being plotted here. It doesn't matter what, but the Balance law say that that it should be somewhere here, and there is a very outlier for this numerical simulation, and clearly there's something wrong up here. And then we could also say what was wrong. It is pointed out up here that in fact that the orbital frequency was wrong, and then made the metadata file, and therefore that correcting it brought down the error. So basically, it is not a general, completely general tool which just immediately tells you what is wrong. But it spots first that there is something wrong. And then you have to think a little bit about, that particular region of the parameter space, that particular numerical evolution, or that particular binary waveform model to say how it could be corrected. So we do offer hints, but it's not kind of a simple machine, simple crank that you can turn out. But understanding the balance laws and understanding the model a little bit does lead to concrete suggestions for improving the model.
Thank you very much.
You're welcome.
More questions. So maybe before you come up with new question, I ask a question again. Why this term memory effect is so well known in string community, holographic community? Why is it so fashionable? What's so special about the memory effect?
Yeah, okay. So now I'm going to make some remarks which are very personal, which are that when I was a younger person growing up these things, I knew about memory effect, this memory thing when I was just started working in this thing, right? In the late 70s, early 80s, I already knew about this thing. And people like Ted Newman knew about it completely. There's no question about it. It's just that nobody pinpointed it as a memory effect. They didn't call it nonlinear memory effect somehow. So the reason why there is so much interest in the community of the more particle physics or community which comes from particle physics is the following. That memory has to do, okay, so this is the flux of the supermomentum, and you can see that there is a term which is quadratic. This is called the nonlinear term, and this is often attributed to Christodoulou, although, this formula have appeared in the literature quite a long time ago, and Freundiner had written a clarifying paper relating what Christodoulou was saying with what the older literature. But it is this term which is absent for ordinary translations. Why is it absent for ordinary translation? Well, if in fact this were if in fact this were alpha of theta and phi, which is to say the linear combination of the first four YLMs, translation, then I could just integrate this h squared. I can take it out here. I could just take h squared here, and h squared of f is in that case 0. Therefore, that is the reason why for translations, this term is absent. We saw that already here when we did the translations balance law. I hope that doesn't matter. That term is absent for translations, okay? It's absent for translations just because h squared of this is equal to 0. So but it is not 0 for super translation. So it is really characterized with super translation. Now, the reason why it is important is because this term, as you might remember in the 1980s, I showed that this is related to the infrared issues, infrared divergences in quantum theory. I call them that you have got these various derivative operators, which is like sigma, and then I said that there are vacua. The vacua are the derivative operators for which there is no radiation. So psi 4 naught, psi 3 naught, imaginary part of psi 2 naught all vanish. News vanishes for these ones, and they differ from each other by super translation. And that in fact, these presence of these inequivalent vacua tell us that the Fock representation is not enough. If you want to accommodate inequivalent vacua, then you must use non-Fock representation in infrared sectors. And this is what was pointed out, I pointed out in the 80s, not a long time ago. But more recently, like 10 years ago, or maybe a little more than 10 years, not 10 years ago, people like particularly Andy Strominger recognized that this is something to do also with the with the soft theorems, which had to do with infrared problems that Weinberg had proved long time ago. Now, the soft theorems and all that thing has to do with perturbative gravity. What I had shown was true in full non-perturbative gravity. But still, because people are used to the soft theorems, to infrared problems, and so on, that is why the memory is so important. The memory comes from the soft term, as they call it, because it's only linear in news, and it is there only for translations. Because it is only linear, I can integrate by parts and kill it if it is a translation. So that is why it is important. It is really because of the infrared issues that people are interested in.
Okay, thank you. So, are there more questions?
There is one clarification I would like to make if there are no questions.
Yes, yes.
And that clarification has to do with what people call peeling theorems. Now, I began this whole discussion with Maxwell theory and the peeling, and then I introduced psi4 naught, psi3 naught, psi2 naught, etc., using the peeling properties. These peeling properties assume that it assumes that the conformally rescale metric so this is a physical metric, the conformally rescale metric, they assume that it is C4. Why C4? Because first of all, the wild tensor has to be well defined. So that says that this must be C2. But we know the wild tensor is well defined, and it is actually 0. And therefore, in fact, omega to the -1 times the wild tensor is well defined. To do this, I had to do Taylor expansion, and therefore I have to assume that the metric up here is actually C3. So this requires G to be C3. And then finally, in the balance laws and various other things, one uses the Bianchi identity with respect to this with respect to this KB. So because I'm taking a derivative, that means that G has to be equal to C4. So the standard Newman-Penrose framework or Penrose framework and so on and so forth that goes through completely with the metric is C4. But various people have argued that generically the metric would not be C4 at Scratch. And particularly this was sort of brought to forefront by seminal papers due to Christodoulou and Kleinemann. Now, all this work has to do with vacuum general relativity and vacuum general relativity with R4 topology. So, strictly speaking, this really does not apply to what happens if you have matter sources, or does not apply to black holes, because topology is not going to be R4 up here. But nonetheless, this provides a lot of intuition and people take this very seriously. So the question here was about, the question was that what they showed was that in fact, you can give yourself a Cauchy data on a space-like surface, which is close to Minkowski space in some function space sense, for which the evolution will give you the entire global evolution. So it's a global result about existence, which is very non-trivial. So, and this is for nonlinear. So there is a nonlinear neighborhood of Minkowski space, nonlinear in the sense that I'm not doing a linearized approximation, in which the solution exists everywhere. But what they found was, for which there's a global solution, but they found that the global solution is not C4. They found that psi4 not exists in Newman-Penrose language, psi3 not exists, psi2 not exists, but psi4 not does not exist. It blows up at scrapless. And similarly, sorry, this was psi1 not, and I'm not psi4 or psi3. but psi1 naught does not exist. Oops. And similarly, psi naught doesn't exist. They don't exist. And that sort of became a kind of a intuition mantra in the mathematical relativity community that peeling does not hold. But there are also theorems due to Crucial, Piotr, and Daley, which say that in fact the metric, you can give initial data, evolve, and get a metric. So the conformally rescale metric GAB would be CK for any k, any finite k. Of course, these data are therefore, as you can imagine, the data that these people use are more restrictive than the data these people use. And the whole thing has to do with, is it reasonable to choose data so that the metric is C4, or is it not reasonable to choose data? And there is a lot of discussion on this. There was also an early discussion by, in a paper, very early paper by Blanchet and Damour, in which they did post-Newtonian expansions and found that at Scry, there is a problem, that the metric is not well behaved. But then later, Luc Blanchet, and he explains this in his review paper very well, showed that, in fact, there is no problem, but it is because they were using certain coordinates, harmonic, if I remember well. But if you went to the Bondi-Sachs type coordinate, then in fact, the metric is perfectly fine here in the post-Newtonian theory. And that is what is used in post-Newtonian theory, that the metric is perfectly fine up here. But there is always some tension about whether, in fact, the metric is sufficiently regular here for the peeling to hold. If psi1 naught were not to exist, then the total angular momentum, which we did not discuss on a cross-section of Scry, would not exist. And that is not something that, for example, then LIGO could not claim anything about the angular momentum here, or angular momentum of the remnant, and so on and so forth. So I think that physically, the statement is that I think that psi1 naught is going to it does exist in my view, and therefore, if at least for compact binary coalescences. Now, what would happen if you actually had a scattering situation in which two black holes come in from infinity and go out to infinity? In that case, I think there are indications that psi1 naught by itself would not exist, but the divergences in psi1 naught are in higher LM nodes. So divergences in psi1 naught will be so scattering situations. I think that psi1 naught would have problems. But these are for L bigger than 2. For L equal to 0, there's no problem. And for L equal to 1 also, there's no problem. And the point is that now what I'm saying up here is my current expectations that there will be no problem for psi1 naught for L equal to 1. And what enters in the angular momentum formula is only the L equal to 1 mode. So I think it is true. It is likely to be true. I don't know if it's true, but that for scattering situations, psi1 naught may not exist. And but on the other hand, L equal to 1 part, which is what angular momentum cares about, does exist. But it is interesting that in this case, the peeling may not exist. Peeling may not hold in this particular case. So I just wanted people to know this because you probably hear very contradictory statements about peeling. And this is the very short summary of it. I think we're gone on sufficiently long, but if there are questions, I can answer them. But if not, we can call it a day.
Okay. I don't see any more questions, so let us thank Abhay again.
Okay, thank you.
Thank you.
I've sent the today's lectures in the email. So I think that the participants should get them soon.